Yeah, hi everyone. My name is Zhu, a fourth-year PhD student from Princeton. I'm very happy to present our recent work, REITS, Reflective Surface for Intelligent Transportation System. This paper is a joint work with my colleague Chen and our advisor Sigurd, James, Naveen, and Kyle. As we know, self-driving cars are predicted to dominate the transportation industry in the foreseeable future. So by 2035, 75% of car sales will be cars with self-driving features. In order to get widespread adaptation, self-driving car must meet very high safety standard. Typically, it has to achieve the fatality rate of less than 1 for every 100 million miles driven. In order to make the self-driving car safe, the vehicle must sense the environment reliably. For example, it has to detect the other vehicles and the pedestrian. Radar is one of the most important techniques that self-driving cars use to sense the environment. For example, in this figure, a typical self-driving car has multiple radars. There is a one long-range radar in the up front to detect the object along the path, and there are also multiple short or medium-range radars to detect objects surrounding the car. In this paper, we focus on improving the reliability of radar-based sensors for self-driving cars. Before talking about the design, let me introduce a little bit background about how FMCW radar works. Suppose we have two cars. The left car wants to detect the distance between the right car and itself. In order to detect the distance, it will shoot a signal towards the right car and capture the reflection signal. The figure on the right shows a typically detection signal. The term FMCW is a short for frequency modulated continuous wave, which means the signal actually shifts the frequency across the time. We also call it a chirp signal. In this curve, the blue line is a transmitted signal and the red line is the received signal. Notice that there is a gap between the transmitted signal and the received signal. Radar actually can use the gap to detect the object. Specifically, radar calculates the distance as shown in this formula. D equals FBU times D divided by 2K. Here, D is the distance between two cars. BU is the gap between these two chirps. And the C is the speed of light. And the K is the slope of this chirp. However, in reality, the detection is not as perfect as shown in the previous example. If the surface of the object is not perpendicular to the incident wave, most of energy will be reflected to another direction. That means the radar cannot receive the reflected signal, and the left car cannot detect the right car. So in this case, this will trigger a traffic accident. Actually, the orientation of an object determines the amount of signal reflected to the incident direction, which further determines whether the self-driving car can receive enough signal for radar detection. If the object happens to add a very bad orientation for reflection, it can lead to the failure of self-driving car radar, which also incurs accident. As we talked before, self-driving car must reliably detect the object of interest, regardless of the orientation of target object. Our solution is to attach a surface to the target object so that it can always reflect the signal back to the incoming direction. In addition, our design has two constraints. The first constraint is the surface should be compatible to existing radar system, regardless of its modulation or track time. The second constraint is low power, since the surface should also be deployed with pedestrian or on the road infrastructure. Some of them may not come with a large power source. That means the surface cannot use active electronics like power amplifier, so it cannot transmit signal actively to make the radar system detect. In this paper, we use a technology called Van-Enter array in our design. The left figure shows an example for a four antenna Van-Enter array. So if we, as we know, radar is typically in the far field of the surface. So we can view as the incoming wave as a plane wave. If we take a plane which is perpendicular to the signal propagation path, so as a reference plane here, the incoming signal at the reference plane should have the same phase at all different points, because it actually travels through the same distance from the signal source. In this example, after passing the reference plane, the incoming signal can travel through two paths. The first one is from the reference plane to the antenna A1 and through the transmission line S1 and to the antenna B1 get transmitted by the antenna B1 and return to the reference plane. And the second path is to the reference plane to A2 to S2 to B2 and go back to the reference plane. So if we compare the length of these two propagation paths, we can see that the part of propagation path that is over the air actually have the same length due to some geometry. The same length in summation. The only difference is the transmission line length. So if we can set the transmission line length difference to be lambda, where lambda is the wavelength, that means if the signal have the same phase at these 2 points, and after go through the propagation path, it will also have the same phase at these 2 points when returning back to the reference plane. So, which also means when the signal return back to the radar receiver, it will also have to have the same phase. So that means this kind of array actually blindly beamform the signal back to its incoming direction. So for one-dimensional array, we can have a design, as we said before, to beamform the signal back to its incoming direction. However, what we need is actually a two-dimensional surface, which can beamforming. So by working out some geometry and math, we found that all pairs of antennas can still beamform together as long as the deployment of the antenna pairs and the transmission lines follow the following two requirements. The first requirement is all pairs of antenna should be central symmetric to the same central point. And the second is the length of any two transmission line differs by k lambda, where k should be an integer and the lambda is a wavelength. So we can design our surface as shown in the right figure. First, we place all the antenna pairs on the concentric circles. The radius difference between two adjacent concentric circles is k lambda times k times lambda divided by pi. So this makes the half lambda length differs by lambda, which is a wavelength. And then we can connect any two pairs of antenna with transmission lines. Then we can get a good beamforming surface to beamform the signal back. In addition, we also want to modulate some information with the surface so that the radar system can detect such kind of signal. For example, we can let the surface transmit whether the attached traffic sign is a stop sign or a speed limit sign. In order to do that, we insert an alternative path to the transmission line of each pair of antennas. The alternative path is half wavelength longer than the original path. With the surface switch to choose the original path, the whole system still beamforms the signal back. However, when the surface switch to choose the alternative path, the transmission line length of old path is still the same, but the transmission line length with the even path added by half lambda. So the signal from the even path, the signal travels through the even path will cancel out with the signal that travels through the old path. In this case, then the radar cannot receive the signal reflection. So with this mechanism, the surface can modulate on-off keying informations and let the radar detect identification information by switching on and off. Our REITS surface can be deployed for 3 applications in the real-world scenario. The first is the REITS system can be deployed with a traffic line. It can help the self-driving car detect whether it is in the correct traffic line, even if it's foggy or it's raining heavily outside. And the second is the deployed with the vehicles and the pedestrians. It helps to alert other vehicles to avoid traffic accidents. And the third is to be deployed with a traffic sign. For example, in this picture, it can help the self-driving car knows the speed limit of this road. Then we show the preliminary result for the design of REITS. So on the 3 figures, we evaluate a near-field electric patterns with a CST simulation software for 3 cases. The first is a pure metal baseline, and the second is a REITS tag when we tuning the state to be constructive, which is beamform the signal back. And the third is destructive case. It's also a REITS tag when we tune the switch to cancel the signal out. From these figures, we can see that we actually set the incoming signal direction to 30 degrees, which is plotted in the white arrow. For the meta baseline, we can see that most of the energy is reflected to the direction of minus 30 degrees, which is another direction from the incoming signal wave. However, for the constructive case, most of energy is actually reflected back to the incoming direction. And for the destructive case, rays actually create a null at incoming direction. So by comparing with these 3 figures, we can show that REITS has a very high effectiveness in the manipulate the reflection. We also evaluate the performance of REITs at a different distance. In this figure, the x-axis is the distance between the REITs tag and the distance between the REITs tag and the radar, and the y-axis is the relative amplitude of the signal. So in this figure, we have 3 lines here. The blue line is a result from the REITs when tuning to the constructive state, and the blue line is the result from the also from REITs when tuned to the destructive case, and the gray line is the metal baseline. So from the figure, we can see that REITs actually can achieve consistent high gain compared with the baselines over distance. Specifically, it can have a signal boost compared with the metal baselines by 11.2 dB, and the the signal strength difference compared with the destructive case with 12.2 dB. In addition, we also study whether we can achieve better performance gain if we add antenna into this system. In this figure, we have x-axis is the number of antennas, and the y-axis is the relative signal amplitude. The gray line is the theoretical upper bound for scalability by adding antenna, which is the signal amplitude increased linearly with the number of antennas. So basically, this is if you add more antennas, the assumption of this line is all these antennas can beamform the signal with 100% of efficiency. So the signal actually add up linearly together. The red line is the reflective signal amplitude for REITs with different number of antennas. So the blue line is the reflective signal amplitude for metal, which with the same area of corresponding REITs element. We can see that REITs actually scale approximately to the theoretical upper bound. However, the metal baseline did not scale up, even if the area increases. The result fully demonstrates the scalability of REITs and in contrast with the metal baselines. Yeah, thank you for listening to this talk.